This is a video presentation of the MEng project concerning the bilateral teleoperation of a robotic manipulator using virtual reality and augmented reality tools. Recently, the UK has been tasked with the decommissioning of its first generation of nuclear facilities, which date back to the atomic weapons program of the 1950s. These facilities have reached the end of their operational lifetime, and the transition into the post-operational cleanup phase has begun. Decommissioning these legacy facilities costs the UK taxpayer around £3 billion a year, and these activities are expected to span the next 120 years. Current decommissioning techniques, such as nuclear glove boxes, are outdated and potentially harmful due to the close proximity of the human operator to the hazardous nuclear material. This project is motivated by the urgent need for replacement for these decommissioning techniques that could improve safety and reduce the operational costs. This project involves the fusion of two exciting fields of robotics, teleoperation and haptics. Teleoperation concerns the remote control of robotic manipulators through communication channels. It allows the user to control a remote robot without exposure to the hazardous environment. Haptic technologies recreate the sensation of touch by applying forces or vibrations to the user so they can feel virtual objects in reality. A haptic glove controlling a robotic manipulator could couple the dexterity of the human body with the resilience of machinery, thereby creating an invaluable tool for nuclear decommissioning. Supplementing this system with vision capabilities through the use of VR or AR tools would allow the user to feel present in the robot's environment. This project aims to develop an innovative system that combines telerobotics and haptics to provide a novel solution to the complex challenge of nuclear decommissioning. The haptic glove market is growing rapidly and is expected to be valued at $4.8 billion by 2030. In the industry currently, companies like Haptex provide the user with accurate tactile feedback at the fingertips. Dexter Robotics built a lightweight, versatile, and wireless exoskeleton, and most recently the Tesla Suit glove has been developed, which looks to create a more immersive sensation of touch. The glove in this project incorporates features from these designs and others to develop a solution for nuclear decommissioning. However, this technology can be extended to surgical procedures and immersive gaming, to name a few alternative applications. After careful consideration of current designs and the project outline, the implementation of the project was divided into 6 technical sections. The block diagram shown details the interrelationship between these technical sections. A one-finger prototype was developed, which was then extended to a full 3-finger exoskeleton design in a CAD software. The exoskeleton was designed to house all of the accompanying electronics. Servo motors were used with a 2-gear mechanism to implement force feedback in the design. The designed PCB was also placed on the CAD model. Encoders placed above the knuckles were used to measure the joint angles of the user. The discrepancy between the user's joint angles and the position of the robotic gripper was then used as an input to the control system in order to implement accurate force feedback. This also ensured a high tracking performance of the robotic gripper. A full duplex Bluetooth communication was used to communicate between the exoskeleton and a computer in the user's environment, and a wireless connection over the internet was used to connect the two computers in separate environments. A VR system was designed to allow the user to have a 3D view of the robotic manipulator's environment. The glove was also equipped with a HTC Vive tracker for motion tracking of the user's arm. A color depth camera was used to map the robotic manipulator's environment. It provides a synthetic view of the robot's environment in the form of a 3D point cloud. 2 systems were integrated to outline the teleoperation process. The robot operating system shown in the Gazebo software to simulate the robot nuclear environment, and a virtual reality system shown in Unity 3D, which visualizes the robot environment using a virtual reality headset. The HTC Vive controller specifies the desired location of the robot. Once the robot has moved to the right location, the controller closes the robotic gripper to pick up the object. The field of view within virtual reality was controlled to provide optimal visualization of the environment. The user then controls the robot to move the virtual object between 2 tables. The system moved the object 0.9 meters in 44 seconds. The robotic gripper is then opened to release the virtual object. In future work, introducing thermal haptic feedback by adding temperature-sensitive actuators along the lining of the exoskeleton design would allow the user to perceive the temperature of objects they interact with. Additionally, once the exoskeleton is developed, user feedback trials could be held to identify areas of improvement in the design. The implementation of these improvements could increase user satisfaction with the product.